Hi everyone. This is a look at communicating enthalpy change, communicating delta H. Delta H can be communicated to us in a couple of different ways. We might have a balanced chemical reaction with the delta H on the side, separate from the reaction. Or the energy, the enthalpy change, the delta H, it can be written right into a balanced chemical reaction itself. Let's take a look at our two main situations, an endothermic or exothermic reactions. Both of these types of situations can have, like I just said, delta H on the side or the energy included right in the reaction. These two situations are the exact opposites of each other. Let's start with endothermic. In an endothermic reaction, the delta H is positive. Energy was gained, energy was absorbed, energy was taken in. It was endothermic. If we're going to write the energy in the reaction itself, we're going to put those kilojoules on the left-hand side of the reaction before the arrow, like the energy was a reactant. Energy is going into the reaction. It's a gain, it's endothermic. Let's look at this example. We have a balanced chemical reaction here between mercury and fluorine. We have the delta H on the side, separate from the equation beside it, explicitly being shown delta H equals positive 117 kilojoules. I'm calling that delta H beside the reaction. But the whole thing could get rewritten where the energy is included in the reaction itself. We're going to put the energy on the left-hand side. A positive delta H means it's endothermic, and the energy is like a reactant before the arrow. There it is. So mercury and fluorine and that energy all react together to produce our product. The energy does not have to be the last term before the arrow, but it does have to be on the left-hand side of the equation. Exothermic reactions are the exact opposite. This time, the delta H is negative. Energy was lost, energy was released, energy was freed, energy was liberated, energy was given off. It's a negative value for the delta H. And when it's beside the equation, we can specifically see that negative sign. If we're going to rewrite the equation, including energy right in the reaction, it's going to be on the right-hand side of the equation after the arrow, like it was a product. Here we can see methane reacting with oxygen to make carbon dioxide and water. And there's the delta H on the side with that explicit negative. When we rewrite the equation, there's the arrow, energy shows up after the arrow. It doesn't have to be the last term in the equation, but it does have to show up on the right-hand side after the arrow. One small thing to be careful of. It looks like the negative became positive. It's very tempting for students to want to put a negative sign right there again. Don't. Sneakily, that is not a plus sign, even though it looks like it. This is saying that methane and oxygen react together to give off carbon dioxide gas, water vapor, and that energy is being given off. It's on the product side of the equation. There's two different ways we can communicate enthalpy change. We might have delta H beside the reaction, or have the energy, the enthalpy change, the delta H, included right in the reaction itself. We can do this for both endothermic and exothermic reactions, and they are the exact opposites of each other. Delta H is positive, delta H is negative. We write the energy on the left as a reactant. We write the energy on the right as a product. It's all about the side of the equation that the energy appears. Really watch your exothermic ones. That negative feels like it turns positive. Be a little bit careful there. And I hope that helps.